This video explores the combined use of joints and constrained components within an assembly. We will highlight the functionality of each method and their respective strengths in various scenarios. This wireless speaker assembly features inserted components, indicated by the chain link icon next to each component listed in the structure browser. Because the components were inserted into the design, there are currently no assembly relationships between the components. This is where we will use the joint and constrain component commands. The speaker body main brace component is currently grounded to the top-level parent assembly, as indicated by the anchor icon next to it. This grounding prevents the component from moving. All other components in the assembly are currently free to move. To begin, we'll use the joint command to position one of the speaker mounts. The joint command works by selecting a snap point to create a joint origin on the component you want to move, and then connecting that joint origin to a snap point on the destination component. For this step, we'll select the circular edge of the hole on the front face of the flange to establish the first joint origin. Observe the joint origin icon, noting its X, Y, and Z orientation, as we want the destination to match this. Next, hover over the circular edge of the hole on the main body where the speaker mount will be connected. Ensure the joint origin icon displays the same plane orientation, which is the desired alignment. Then click to select the edge. The speaker mount will then move into the position, correctly oriented. In the Motion tab of the dialog, we can observe that the motion type is currently set to rigid. This setting has effectively restricted all degrees of freedom, preventing any translation or rotation along any axis. This means that the speaker mount is now rigidly joined to the main body. This demonstrates the speed and efficiency with which the joint command can be used for part positioning. By selecting the circular edges of the components, we achieved both axial alignment of the circles and alignment of the planes on which these circular edges lie. The speaker can be quickly positioned onto the speaker mount by repeating this process. Note how efficiently the joint command achieves this positioning. By changing the motion type to Revolute, 1 degree of freedom is opened, permitting rotation around the referenced circular edge. Ensure the setting is returned to rigid to lock all degrees of freedom. Next, we will use the Constrain Components command to position the second speaker mount and speaker. Unlike the joint command, which locks down all degrees of freedom first, and then selectively opens the 1 or 2 needed, Constrain Components locks down each degree of freedom individually using separate constraints. To begin, we'll select the cylindrical holes on both the speaker mount and the main body. Dragging the speaker mount will demonstrate the initial cylindrical constraint that was created. This constraint allows the part to both rotate and translate along the axis of the selected cylinders. To further restrict the movement, edit the constraint feature from the timeline. Add a second constraint by selecting another pair of matching hole cylinders, one on the mount and one on the main body. With this addition, the speaker mount is now prevented from rotating, as that degree of freedom has been locked down. It can now only translate. Finally, eliminate the translation degree of freedom by adding a third constraint. Select the front face of the flange and its corresponding mating face on the main body. The part is now rigidly constrained and completely locked in place. Constraining components is similar to real-world assembly. You define the desired alignment, such as line up this hole with that hole, followed by establishing contact, like push these parts together until they touch. For a clearer understanding of the relationships created, navigate to the browser's Relationships folder, expand Constraints, and then expand the last constraint. Clicking on each constraint will graphically highlight the specific features on the components used in its creation. This visual feedback is often simpler to interpret than the less descriptive joint icon used with the joint command, which doesn't graphically illustrate the jointed features. The great thing with Fusion is that you can use either joints, constrained components, or both in the same assembly. Depending on the scenario, using joints may prove to be the quicker option, while other times, constrained components will be more effective for positioning parts compared to using joints. For example, we positioned the speaker mount with constrained components, but we can also use joints to position the speaker. It doesn't matter that we're using both in the same design. Notice that it only took one selection to position the speaker using joints. You can make constrained components behave more like joints by adjusting your selection method. Similar to the joint command, instead of selecting faces, selecting circular edges on two faces will align the center of the circles and the planes they lie on simultaneously. This is how we'll position the final speaker mount. By selecting a circular edge on the mount, and then one on the main body, you'll see that it restricts 2 degrees of freedom, resulting in a revolute motion rather than a cylindrical one. To completely lock down the remaining degree of freedom, one more constraint is needed. You can position a component using a joint and a constraint simultaneously. For example, we'll use a Revolute joint to place the speaker onto its mount. Note that the speaker is initially at an awkward angle, so we'll apply a constrained component to align one of the speaker's holes with a corresponding hole on the mount. The Revolute joint allows the speaker to rotate until the holes are perfectly lined up. Constrained components is particularly useful compared to joints when dealing with parts that are curved or lack readily identifiable snap points, such as the trim piece that needs to be attached to the outer shell. The process involves selecting the curved side face of the trim piece and then the corresponding mating face on the top of the shell. Initially, if you attempt to move the trim piece, the shell will also move because it hasn't been assigned any positioning relationships yet. To observe the effect of the constraint, we need to first expand the outer shell assembly and pin the main shell in place. With the main shell fixed, dragging the trim piece will now demonstrate how its curved face accurately tracks along the curved face of the main shell. We need to add a second constraint to further restrict the degrees of freedom. Select the curved faces on the front of the trim piece and the main shell. Although the alignment appears correct, it's recommended to test the constraint by attempting to drag the part. Notice that it can still slide vertically. Therefore, we must add one final constraint by selecting the bottom face of the trim and the bottom face of the outer shell. With this step, the trim piece is now correctly positioned and fully constrained. To complete the wireless speaker assembly, we will continue using both the joint and constrained components commands together. Our next step is to position the circuit board onto the back of the inner brace. You may find that using the joint command is more difficult here, as snapping to the correct point is more complicated due to the thin solder mask layer, which may lead to clicking the incorrect snap point. In this situation, it is likely faster to use constrained components, selecting surfaces rather than edges to achieve the desired result. Next, applying the joint command to create a rigid joint with the inner brace immediately fixes the part's orientation. Due to the existing constraint relationships, the circuit board moves along with it. This effectively illustrates how combining both methods can significantly accelerate your design process. Finally, we can position this whole assembly into the outer shell assembly. To improve visibility, We'll turn off the inner and outer grills. We'll use the joint command to create a rigid joint between the inner brace and the main shell. As you've seen, Fusion gives you the freedom to choose the workflow that fits the moment. Joints can get you moving fast, while constrained components offer deeper control when you need it. The real power comes from knowing both, and using whichever approach helps you build smarter, faster, and more confidently.